Hi everyone, I'm Yan Li, a software engineer, and together with my colleague Lingwei, also a software engineer from Meta, we're going to talk about how we build the event-level deletion service. So this is a cross-team work, including the as data privacy and as delivery and storage team. So thanks everyone for the joint collaboration. So now start with a problem space we're dealing with. Every day, billions of users navigate through the internet and they leave the trails of data behind. And they may raise, this is a frequent question to us. How do we build the service to support data deletion, user data deletion? And the tricky part, challenge part of this problem is actually how do we build the deletion service with less cost and do the data deletion as need basis. So now we're getting into the problem, why event level deletion? So in the typical deletion scenario, the solution we built and the options we provide to user can be called something like a batch deletion. This means deleting data that belongs to a certain account, or delete the data, all the data across a surface, or delete data in a certain time range. So the rationality behind this a batch deletion sometimes is because that it's just too hard to identify the specific data we want to delete and delete them fast enough before it propagates into the whole system. So with the growing need to embrace a user-centric philosophy and improve the cost efficiency, we aim to explore a new design with the following focus areas. First, we want to have fine granularity control of the data deletion down to the event level. Then, because it's event level, we want to make it versatile to meet a different purpose, not just fixing for a certain scenario. I just also want to make it fit into the new emerging needs, from the policy or product set need. In this case, to reduce engine cost. Then we also want to reduce the infra cost. Instead of keep increasing the frequency, we do data deletion with more infra costs. We do it on need basis. So now let's get into the technical area that how we build the system. So first, the focus area of this design is the user interaction data that we do not want to propagate being used in the as delivery stack and be getting to the as data storage. So the traditional system have the following insufficiency, such as duplicate input data sources and the overlapping data passing pipelines and free-form data usage. Name example, a user may interact with multiple ads within a certain time range. And these interactions may log into different tables. And they will be parsed aggregate with different time windows and blended with different attributes. So they also be used in the ranking and targeting models and different configs. So we start. This is make the problem space much complicated because there are so many copies of data and kind of difficult to track the usage. So we start with adopting an input closure and output closure system, which means in our new design. So this means that we highly focus on how the data get logged. To constrain the data must only be logged when we clearly know what data it is. And the data getting into a unified data storage, which can be reused for multiple purposes. And in the downstream, it only allows the data to be consumed, to be authorized consumers. So in this way, we reduce the problem space to have less copies across the system. So let's get into the details of how to store the data in make it data reusable. So the data is stored in a heterogeneous representative. All the attributes associated with the user interaction events are stored together. Of course, the critical ones. And then you can see that there's a unique ID to make this user event blob of information trackable and identifiable in the system. Besides that, there's the usage status That could be a default usage status like for all the data or the certain group of data, which does need to be stored in copy. Besides that, we only need a small map structure to store the data which user want to delete in a key pair. So next, let's talk about how we use those data structure and how the data propagate. So you can see in this, the key point of this design is that we quarantine the data before it getting propagated into the data usage and the persistent storage system. You can see in this diagram, there's a typical data incoming real-time ingestion streaming flow, which gets the real-time user data in the heterogeneous data structure with all the critical attributes. And of course, it's stored keyed by unique ID. There's a separate path that sporadically injects the deletion status request, which can be just simply implemented by some kind of RESTful API instead of a data streaming service. And in this unified storage, instead of pre-processing the data, we only parse the data when there's a need to consume the data, such as add request comes to fetch the user's history. So at the time we hit the request, the data is parsed according to the deletion status or usage status, depends on where the request comes from, like which product or which service. In this way, we parse the clean data to the usage data stack and log it into persistent storage. So this parsing at consume time design is made possible not just like a change of design and the pipeline side, but also requires the machine learning side changes. So I'll pass it to Lingwei, a colleague, to cover the next part of the ML side.
Yeah, thank you so much, Yan, for the covering the above sections. I will talk about the current challenges with deletion and how we use ML techniques to resolve those challenges to make deletions possible. On the left chart is kind of the broad infrastructure for most industry settings. I'm using clicks, for example, of events. You can see at the bottom we have some data sources, and we rely heavily on kind of feature infrastructure, convoluted data pipelines to do events data aggregation. The same piece of data is persisted in multiple different places. This makes deletion extremely difficult. If we want to delete one of the clicks on the bottom, we have to leave from a whole bunch of different places. So on the right side, with this new representation, each attribute for a given click is persisted only once, which makes deletion much easier. So let's say if we want to delete the first event, we only need to remove x1, c1, and t1. The same task will not be possible on the left. We would have to, And then also with the right side, instead of relying on feature infrastructure to do data aggregation, we delegate that task to the sequence model, which I will dive into more detail on a later slide. Before I dive in, I just want to define a few key terms and our overall approach. So event I'm referring to can be any interaction between a user and an ad, clicks, likes, comments, etc. An attribute is a piece of information about an event that we're interested in. And then an event-based feature is a list of attributes across different events. For each event type, we experimented with the number of attributes that we're interested in, so the number k, and then the different length of lookback window, n. And we basically did a grid search across different k and n values to find the most optimal setup in terms of model performance and capacity intake. Here is a zoomed-in version of the sequence model I was talking about earlier. It's basically a two-step process where we use the event model to generate attribute embeddings from raw attribute values. And then we use the feature interaction part to transform a list of attribute embeddings into one event embedding. Those event embeddings will be passed into the aggregation module. That's the blue box towards the top, which uses a multi-head attention, which runs multi-head attention along with the event timestamps on the right to produce our output embeddings. So if we have n events, we'll have n output embeddings representing how much each event correlates with the other events. When a deletion happens, we'll delete one attribute from each event feature on the bottom. So k attributes associated with events across k different features will be deleted. We'll have one event embedding will automatically disappear, so will one output embedding. So fewer ads of the same kind will be served to the end user. This screen is blinking. Oh, okay.
Display is working.
Okay. Yeah. So here, just to provide a bit more intuition, on the right I attached a diagram of the encoder module for the popular transformer model, just to provide, because people are familiar with the transformer model. So the event embeddings can be thought of as the input embeddings to the picture on the right. The input embedding for the transformer model are generated from the input sentence, and the event embedding are generated from the input event features. The timestamp encoding on the left can be thought of as the positional encoding in the picture on the right. The positional encoding in the transformer model are meant to provide an order at which the words appear, and then the event timestamp encoding also is meant to provide an order that events appear. So event 1 appears before event 2, before event 3, so on and so forth. I will dive into some of the pros and cons of this sequence model. The biggest benefit is that it gives us an ability to respect user privacy in a granular way. We get a cleaner feature space with less capacity intensive. We have less overhead in case of event deletion. We have a relatively resilient model performance also in case of event deletion. Modeling based on raw events have been quite popularly tested these days, including things like the deep interest network model by Alibaba. Some of the negatives is that this sequence model I described can be quite heavy. It can cause QPS regressions. Bigger models are more memory intensive. There are more hyperparameters to tune, like the N and K numbers I've discussed previously, the number of heads for multi-head attention. To summarize my part and Yan's part, we want to give users the ability to delete past events in a granular level. We utilized event-based feature storage to have a cleaner feature space. Event-based features delegates feature aggregation to the ML itself instead of complicated data pipelines. Cleaner feature space combined with input-output closure and then the real-time data processing allow us to achieve event-level deletion. Yeah, I have questions.